Okay, starts now.
All right, thank you for the introduction. Yes, my name is Yoder. I'm from Liberty University PhD student. Today I'll be discussing some of the work I've done in getting at polymer molecular weight distribution and computational fluid dynamics. So it's no secret that polyethylene is a very common product, right? If you look at any plastic object, you see a 2 or a 4 inside the little recycle symbol. It's a polyethylene product. So because of that, that industry is very profitable and very competitive. So manufacturers are constantly looking for ways to improve their own processes, and oftentimes that looks like cost reductions, waste reductions, or an increase in efficiency. And oftentimes manufacturers want these process improvements without any sort of loss to their own production rates, which is a challenge in and of itself. And then additionally, these process intensifications have also other problems associated with them, including safety risks and other potential profit losses. And those primarily come from the exothermic chemistry of polyethylene. We all know that these reaction rates are non-linearly dependent on temperature. So with exothermic chemistry, reaction rates occur, heat is added, the temperature increases, decreases the reaction rates, and creates this kind of snowball effect called thermal runaway. And if that's not mitigated, we can have reactor failure, which, if not shut down before it reaches some climax, the reactor could explode, and otherwise you have to shut down the reactor, kind of flush all the contents. And that could take an entire day and a loss of hundreds of thousands of dollars for the producer. And so for these reasons, simulation is often preferred for polymerization systems as opposed to experiments when trying to learn more about those systems. Because of that, there's a lot of simulations specific to polymers. They all fall into 3 kind of classes. The first of which is a continuous stirred tank reactor, or CSTR. And this is characterized by no internal gradients or a perfectly mixed reactor, and is transient, but will eventually reach a kind of quasi-steady state. There's also a plug flow reactor, which are typically long, thin reactors that have axial gradients, but no radial gradients in temperature or species, and it's steady state. And then the third general classification is computational fluid dynamics, which has gradients in all directions. You can see some real mixing inside these reactors, but they're significantly more complicated and costly than these other 2 methods. So implementing chemistry in CFD is very difficult, in addition to just the normal difficulty of CFD, such as mesh resolution, finding the right turbulence model, and other subgrid scale models, because you need a transport equation for every species in the chemical mixture. And this is even more difficult for polymers because you need a species transport equation for every chain length of polymer, which is theoretically infinite. And if you look at a realistic polymer molecular weight distribution, this goes up to a couple 100,000, which is still unfeasible computationally. And solving the chemical step in a CFD simulation can be a large portion of the computational cost, sometimes 70 to 90%. Fortunately, the method of moments has been developed in which we can model the transport of these polymer by an average value instead of each individual chain length. And the way these moments show up is by a summation of the concentration of each polymer chain length times that particular chain length to some degree. And with a handful of moments, we can get average properties of the polymer, including the number average molecular weight and the weight average molecular weight, as a function of only a handful of moments and the monomer molecular weight. And we can also get polydispersity index from these values as well. So I briefly wanted to illustrate kind of how this method of moments is implemented in CFD. And to do so, we'll have a simple polymerization scheme where we just have initiation, propagation, and termination reactions, the basis of polymerization. And from these, we can develop chemical source terms. And in this example, this is for the concentration of polymer chain length N. And so from each of these reactions, we have a term in this source term where positive values are when that polymer is a product, and the negative values are when it's a reactant. And each of those terms are formed by the reaction rate K times the concentration of both of the reactants. And that's summed over all reactions to get the rate of change with respect to time of a particular species. So from that, we apply the method of moments. So we take that equation we saw previously and apply this equation, where we multiply the entire thing by the chain length to a particular degree, and then sum that over all chain lengths And then for this one polymer species, we can get 3 different moments just by performing that process. We get 3 different differential equations instead of hundreds of thousands, if not millions. So the method of moments provides average properties for distribution, and it's good for kind of just comparing different methodologies quick, but we necessarily lose with that distribution. However, if we assume the shape of the statistical distribution and knowing the moments, we can kind of plug those into values to reconstruct what that distribution may look like. And to illustrate that, we have some simple example from literature of a particle size distribution that's given moments, and we choose just some different statistical equations. There's Gaussian in there, gamma distribution. And we can see that from the exact same moments, we have different distributions, all following a similar trend, but vary in the breadth and peak location. Unfortunately though, industrial polymer molecular weight distributions are often bimodal, exhibiting this kind of shoulder here, which is like a second mode in the distribution. And so the process discussed previously can't really be applied because the statistical equations are often unimodal and don't replicate that well. But a technique has been developed to take that distribution and split it up into subclasses where you can have moments for each of those subclasses which are separated by degree of branching, and that's what's different in this moment equation relative to what I showed you previously, where we just have this C term here. And so if you can have moments for each subclass and moments for the overall class, create distributions for each of those, and then sum them all together to get this bimodal molecular weight distribution. And that's what's shown here, where you have these dashed and dotted lines are reconstructions of subclasses, and then the solid line is the summation of all those subclasses, and you see that bimodal shoulder that we're looking for. And so we wanted to test this methodology in our own use case. So we started with a simple CFD model where we're trying to replicate a CSTR model in CFD. And so we just chose some simple geometry that's just a big cylinder. Essentially you can see an isometric view down here. We have cold reactants coming on the left, being mixed in this big cylinder here, and then exiting the hot products on the right. So, as previously stated, we desired this CFD model to be like a CSTR, so we wanted it as perfectly mixed as we could. So in this case, numerical diffusion was desired. So we used large, coarse, tetrahedral cells, low-order discretization schemes, K-epsilon turbulence model, things like that. We had a high mixing rate inside this reactor, but it was actually very difficult to get a steady result with this model, as can be seen in this image here, where we have CSTR temperature, change in temperature from its initial conditions for exact same cases, with the only difference being the initial temperature, which only differed by 1/100th of a Kelvin. And we see that there are vastly different responses, where the warm initial temperature case exhibited thermal runaway and just went to thousands of degree Kelvin. The other one kind of didn't react at all enough to sustain that temperature and just fell off to the inlet temperature. And so we found that a PID controller was necessary in order to obtain a result with this CSTR model. And so we simulated the polymerization of low-density polyethylene with this model. We have the elementary reactions I went over in the illustration previously, with the addition of chain transfer, branching, and scission reactions. And here we can see the results of this bimodal reconstruction, where we assumed a Westlau statistical distribution, and each one of these have a different number of classes, where the blue curve is just with no classes, the orange curves with 5 and 10 classes, the green curve. And we see that adding these classes did produce a bimodal distribution, which is the whole purpose of this, but it doesn't exactly look like the shoulder of industrial polymers like we're looking for. And adding more classes increased the breadth of the distribution and lowered those peaks necessarily. So you also wanted to look at the influence of the statistical distribution shape. And so we plotted 10 case class from before with the 4 statistical shapes we looked at previously for the particle size distribution. And we see that the Gaussian in the blue and the gamma in orange show kind of unphysical left tails here, where they have very high values and they should be close to 0. But the Raleigh distribution here showed that shoulder that we're looking for. And yeah, there's a lot of variation with the exact same moments. exact same number of classes, but just different statistical shape. And we can also look at the influence of a weighted sum. So all the data I've shown you so far has just been a raw sum of each of the molecular weight distributions of each class, but we can actually weight the sums. And that's what's shown in this image here. We have the Raleigh distributions in blue and the Westphal distributions in orange, where the dashed lines are the weighted and the solid lines are just the raw sums. And in this case, the weighted sum is based off of a ratio between the first moment of a particular class and the first moment of the overall distribution. And we see that the weighted sum actually smooths the distribution. So if we look at the blue curves here, that shoulder is much less and raised its peak significantly between the two. And that's observed with both statistical shapes. And this weighted sum also provides an indication of the number of classes needed, because the summation of the first moments should roughly equal the first moment of the overall class. So that'll give you an indication of how far off you are with the number of classes you have here. So in conclusion, we see that CFD provides the most accurate and safe method of process intensification for industrial polymer reactors. And this is really only possible by the method of moments. Otherwise, solving hundreds of thousands of partial differential equations isn't really feasible computationally. And by splitting the distribution into subclasses, a multimodal molecular weight distribution is achieved, and that's much more similar to what we observe in experiment and in industrial reactors. So that gives us more accurate predictions of industrial polymer molecular weight distributions in CFD. And we see that additional classes, assumption of the distribution shape, and summation method all influence what that distribution looks like and can be tuned to match whatever polymer you're trying to match. But obviously here there's a trade-off between accuracy and computational cost, because the more moments you add, the more PDEs you have to solve, and you're kind of getting back to where we started in our first initial problem. So obviously a trade-off here, but significant computational cost savings. So in the future, we hope to validate this distribution reconstruction methodology in the CSTR by looking at industrial distributions, comparing it with plant data, and hopefully determine the appropriate number of classes we need to replicate that, what best method is for summation, and what statistical shape provides the best match. And then take that methodology and implement that into a plant scale reactor model in CFD. Do the same thing there, validate results, make sure we're still spot on relative to our industrial partner, and then perform those industrial process intensification processes to improve that reactor process. So that's all I have today. I'd like to thank my sponsor, Westside Chemical, Liberty University, for helping with this, and I'm happy to answer any questions.
Thank you.